Download this code from codegive.com, link in the description below. OK, let's dive into a Python trick that's surprisingly underutilized yet incredibly powerful, using descriptors for attribute management and validation. While many Python developers understand the basics of classes and objects, descriptors offer a deeper level of control over attribute access and assignment that can dramatically improve code readability, maintainability, and robustness. I'll explain it in detail with code examples. What are descriptors? At their core, descriptors are Python objects that define how attribute access, getting, setting, and deleting, is handled within a class. They essentially intercept the default behavior when you try to interact with an attribute on an object. This interception allows you to implement custom logic for validation, transformation, lazy loading, or any other operation you can imagine. Why are descriptors useful? Encapsulation and abstraction. Descriptors help you encapsulate attribute-related logic within a separate object, making your classes cleaner and more focused on their core responsibilities. Attribute validation. You can enforce data type constraints, range limitations, or any other validation rules whenever an attribute is set. Custom attribute access logic. Implement lazy evaluation, computed attributes, or access-controlled attributes. Reusability. Descriptors can be reused across multiple classes, promoting consistency in how attributes are handled. Readability. Well-named descriptors can make your code easier to understand by explicitly stating the intent behind attribute management. The descriptor protocol. Descriptors are defined by implementing one or more of the following methods, which make up the descriptor protocol. *__get __, self, instance, owner, called when an attribute is accessed, i.e., you try to read the attribute's value. *self, the descriptor instance itself. *instance, the instance of the class where the descriptor is an attribute. If the descriptor is accessed from the class itself, not an instance, instance will be none. *owner, the class where the descriptor is an attribute. *__set __, self, instance, value, called when an attribute is assigned a value, i.e., you try to set the attribute. *self, the descriptor instance. *instance, the instance of the class where the descriptor is an attribute. *value, the value being assigned to the attribute. *__delete __, self, instance, called when an attribute is deleted, i.e., you use del. *self, the descriptor instance. *instance, the instance of the class where the descriptor is an attribute. Types of descriptors. Data descriptors. Implement both ___get __, and __set __, or __delete __. These have the highest priority when attribute access occurs. Their __set method is what allows them to control attribute assignment. Non-data descriptors, aka read-only or overriding descriptors, implement only __get __. They are used for computed properties, lazy loading, and other scenarios where you want to customize attribute retrieval but not necessarily control the assignment. If an instance's __dict _ contains an attribute with the same name as a non-data descriptor, the value in the __dict _ takes precedence. A concrete example, validating ages. Let's build a descriptor that ensures an age attribute is always a non-negative integer. Explanation *. One non-negative integer class *. This is our descriptor. *__set _name __, self, owner, name. This special method is called when the descriptor is assigned as a class attribute. It's relatively new in Python, introduced in 3.6, and is a very elegant way to avoid hard-coding the attribute name. Owner is the class where the descriptor is being used, and name is the name of the attribute, example age. We use self.private_name to store the actual value of the age on the person instance, using a naming convention to indicate that this attribute should not be directly accessed from outside the person class. This is crucial for preventing bypassing the descriptor logic. *__get__, self, instance, owner. This method is called when you access p1.age. If instance is none, accessed from the class, we return the descriptor itself. Otherwise, we retrieve the value from the instance's hidden attribute, example _age. *__set__, self, instance, value. This is the heart of the descriptor. It's called when you assign a value to p1.age equals. First, it checks if the value is an integer. If not, it raises a type error. Then, it checks if the value is non-negative. If not, it raises a value error. Finally, if the value is valid, it stores it in the instance's private attribute, _age. Person class *. The person class uses the non-negative integer descriptor for its age attribute. When you declare age equals non-negative integer, you are creating an instance of the descriptor and assigning it to the age attribute of the person class. 3 Example usage *. The example code demonstrates how the descriptor enforces the validation rules. Trying to assign a negative age or a non-integer age will result in an exception. Important notes *. Private attributes * using a private naming convention, example _age, is important. It doesn't actually prevent direct access, but it signals that the attribute is intended for internal use and should not be directly modified from outside the class. This is a crucial element of encapsulation. Without it, you could bypass the descriptor's validation by directly assigning to p1_age. *_set_name__. This method is relatively new but greatly improves the reusability of descriptors. Without it, you'd have to hard-code the attribute name within the descriptor, making it less flexible. More advanced examples *. Here are some ideas for other descriptor implementations. 1. Type checked attributes *. A descriptor that enforces a specific data type. 2. Read-only attributes, non-data descriptors. 3. Lazy loaded attributes *. A descriptor that only computes the attribute's value the first time it's accessed. Key takeaways. Descriptors are a powerful mechanism for controlling attribute access in Python. They allow you to implement custom validation, transformation, and access logic. Data descriptors, __get__, and __set__, have higher priority than instance attributes. Non-data descriptors, __get__ only, are suitable for computed properties and lazy loading. Use private naming conventions, _attribute_name, to avoid bypassing the descriptor logic. *_set_name__ improves the reusability of your descriptors. Consider using descriptors when you need to enforce consistency and maintainability in how attributes are handled across your classes. Why are they underutilized? Complexity. Descriptors can initially seem complicated. It takes some effort to fully understand the descriptor protocol and how they interact with attribute access. Alternative solutions. For simple attribute validation, many developers might opt for simpler checks within __init__, or using properties. Lack of awareness. Many Python developers simply aren't aware of descriptors and their capabilities. By mastering descriptors, you'll gain a deeper understanding of Python's object model and unlock a powerful tool for creating cleaner, more robust, and more maintainable code. They are a valuable technique to have in your toolbox when you need precise control over attribute management.